everyone. We are going to be looking at the gravitational force, and it's so exciting because you've heard bits and pieces, and now we're going to put it all together, and it's going to be lots of fun. So, have you ever thought about why will an object, when it's thrown in the air, come back to Earth? You all know it happens, and you've all heard the saying, what goes up must come down. But why? Why does it come down as fast as it does? Why does it stop when it gets to the top and then comes down? Why are we stuck on Earth? Why can't we just jump into space? Well, we wouldn't be able to breathe in space, but that's besides the point. Okay, so that's what we're looking at. We're looking at gravitation, so we're going to look at Newton's law of universal gravitation. We're going to look at the equation, which is a little hairy, but we're good. We're going to look at the difference between little g and big G. We're going to look at the graphs associated with this, and then we're going to look at different types of questions, because there's lots of ways we can ask this. Our key words are Newton's law of universal gravitation. On that note, we know that there's 3 Newton's laws. First law, second law, and third law, okay? This is like a 4th law, but it has a special name because it's to do with gravitation. All right, so you need to be careful. We also use the word universal in the title because at our current understanding of the universe, this law works anywhere. Whether you're on Mars, whether you're on the moon, Earth, whatever, according to what our current understanding is. Maybe that'll change, who knows? That's why it's universal. We're then going to talk about the concept of gravity and the universal gravitational constant. We don't like constants, but it's okay. Let's start with Newton's law. You all know the story, I'm sure. Somebody's told you we have no, it was Sir, he was a knight, Sir Isaac Newton sitting under a tree, and then the apple fell on his head, and he went, ooh, gravitation. Not really the way it happened, okay? He was sitting under an apple tree, and then he watched how the apples fall to the ground, and being the incredible scientist he was like, why did that happen? And then he started doing investigations. He then came up with the law, which is a little long-winded, but it's fine. And he said that each particle in the universe attracts every other particle. You have to say attracts with a gravitational force. We're saying gravitational force because we also get electrostatic forces. That is directly proportional, whoopsie, there it is, to the product of their masses, product very important there, and inversely proportional to the square of the distance between their centers. Often with this one, we forget about the fact that it's the product of their masses and it's the square between their centers. That last part between their centers is really, really important. For big objects, where their center is, makes a big difference into the force of attraction that will be felt. Okay? Now, we're going to look at the equation. The equation looks far more complicated than it is. The nice thing, it's on your information sheet. So it's F, force, G, M1, M2, and R squared. Let's go through what each of those mean. So F is force. That's nice. Measured in newtons. That's easy enough. G is a constant. And G is 6,67 times 10 to the minus 11. It's tiny, but it has to be there. And we will investigate it where we get the G from, okay? I'm going to come back to the units. Mass is, M1 and M2 are masses. We call them M1 and M2 because it's two bodies, it's two particles. So we have to differentiate between the two. Of course, it's mass, so that has to be in kilograms. And R is the distance between their centers. That must be measured in meters. Here we need to be careful because we're going to get situations where I'm going to give you distances in kilometers. You must then change it to meters. We'll get to that. When we look at the units for G, the units need to give me newtons. So this is newtons, okay, per kilogram to the minus 2 per meter squared. Is that where yeah, then it'll cancel itself out. We're not worried about the units, okay, because it's going to sort itself out along the way. We're going to use that constant often, the fact that G is constant. So keep that in the back of your minds. Then we need to look at the difference between little g and big G. And of course, when we go G and G, little g, big G. Okay, very important. So little g is acceleration due to gravity. Little g is an acceleration. It's not a force. Okay, and little g, that acceleration due to gravity is a consequence of the planet we're on. So it changes. It's completely dependent on the planet. We now need to look at the difference between little g and big G. They're both G, but they mean different things, okay? And it's not just them being different because one's lowercase and one's uppercase. They're different concepts. Let's look at those. When we look at acceleration G to gravity, here, this is an acceleration. It changes depending on the planet, which is what I've got here. And remember, on Earth, acceleration due to gravity is 9,8 meters per second squared. If you go to the moon, which is a 1/6 the size of the Earth, the gravitational force there, the gravitational acceleration you feel, is 6 times smaller than on Earth, which is why people can bounce on the moon, because there's less gravity. G is a universal constant. It does not change. It's the same value no matter where we go in the universe. Same value. We're done with some theory, so we're going to take a short break, and I'll see you in a couple of minutes. Welcome back. We are now going to do some investigation into how we get the equation that we use to work out the force between two objects, all right? So what we're going to do now is we're going to look at what happens when the mass of the two objects involved change. We're only going to look at two objects for now because we want to simplify it. Remember that you are attracted to everything around you, and everything around you is attracted to you. So actually you do like your science book, okay? But let's just keep it as two objects just to simplify it. Here we go. So here we've got two masses, which are quite big, which are being pulled by giants. Let's just go with that. What I need you to take note of, number one, is in the situation I have on the board at the moment, both masses are experiencing the same force, 33,4 newtons. Why are they experiencing the same force? Newton's third law. Okay, every object when a body A exerts a force on body B exerts the same force on body A, but in the opposite direction. So the size of the force they experience is the same. What I want you to take note of is the black arrows at the top, because you can see that the pink mass, which is mass 2, is attracted to the blue one, and the blue one is attracted to the pink one. Here we're using billions of kilograms just because we want a decent size force. Let's see what happens if I take mass 1 and I double its mass. So now I make it 4. If we look at the force, number 1, we notice that it got bigger, but number 2, we notice that it doubled. So it got bigger because the masses are bigger, but it doubled. It got twice as big because the mass was twice as big. So we're going to double the mass of mass 1, and now it becomes 66,7 newtons. So we doubled the force. Let's double mass 2. That means we need to go to 8. Now I've got 133,5. So I had 66,7. I now have 133,5. I doubled the force again. Compared to the first one, the first time we did this, we had 33,4. I've doubled one mass, then I doubled the second mass, so I made it 4 times bigger in terms of all the masses if I multiply them together, and the force became 4 times bigger. That tells me there's a relationship, a mathematical relationship between the force and the masses. We just made the masses bigger. Let's make the masses smaller. So I'm going to reset. We're back to what we started with the 33,4. Let's make mass 2 smaller. Just by 1. Now it's 25 because we've made the mass smaller. Let's make them both 2. It's now 16,7. So I halved the mass, and now the force is half. So the smaller the masses, the smaller the force between them. Mass is important, but it's about both masses. It's not just about the one. That's really important because it tells us we're interacting 2 bodies. Both bodies are important. You can't forget about one. You've got to have them both. Let's put this into some sort of way of looking at it. What we realized is that if I increase mass, I increase force. What we actually say is that force is directly proportional to the first mass times the second mass. I know that feels weird, but both work together. And how do I know it's times? Because I showed you that if I double both masses, force doubles twice. Okay, why? Because I would be going 2 times mass 1 and 2 times mass 2. 2 times 2 is 4. If it becomes 4 times bigger, then force becomes 4 times bigger. Be careful when we describe this. I can't say that it's directly proportional just to mass. Remember, I said to you, it depends on both masses, and they have to be multiplied together. Be careful as well that you don't add the masses. It's got to be multiplied together. There may be situations where your masses are the same. That's fine. Doesn't matter. It doesn't matter about the value. It's about the fact that they have to be multiplied together. So, force between the two objects is directly proportional to the product of the two masses, m1 and m2. Got that one. What happens when we change the distance? Now here the maths gets a little hairy. So we're back here. Let's reset this back to the original, 33,4. I'm going to change the distance. So I'm going to, let's say, I'm going to make them closer together, and let's half the distance. So we're going to go to 2.6, 2.2. It's getting very close because they're very big. There we go. Oh, now look what happened. I halved the distance. So if we're thinking of what we did with mass, when I halved the mass, I halved the force. I've got closer together, but the forces got bigger. Okay, so if the force got bigger, but why didn't it just double? We've done inverse proportion somewhere else before, so why didn't it just double? And this was quite important. Remember when Newton would have done this, he would have done all the calculations by hand. Didn't have calculators, which is scary, all by hand. So this would have taken lots and lots of data and drawing graphs and all sorts of things. But if we think about it again, we've seen that value before, the 133,5. We started with 33,4. Remember when I doubled the mass twice, we made the force 4 times bigger, which is 133,5. Well, I halved the distance, and it became 4 times bigger. Maybe there's a square involved. Let's think about it. Let's reset. Now I'm going to see if I can make the distance twice as big. So I'm going to move him away to that side. There we go. Let's just make him 6. There we go. Let's go him to the other side so I don't get him off the... Ooh, that's 8. I've now doubled the distance. Look how small that force is now. That's significantly smaller. So I went from 33,4 to 8,3. That's a big difference. So by doubling the distance, we know there's an inverse relationship, but I didn't half the force. In fact, it's 4 times smaller. And if some of you have got your calculators out, you're going to go, but it's not exactly 4 times smaller. It's because we're going to 1 decimal place. If we kept all the decimals in, we would see it. But 1 decimal place is enough. I doubled force, doubled distance, and force became 4 times smaller. I'm seeing a relationship because 2 squared is 4. Okay, the square is becoming important. If we look again, just quickly, so let me double this mass 1's mass. We double what that force was. As soon as I make the distance smaller, the force gets bigger much quicker. So distance actually has a bigger role to play than mass, because a small change in distance makes a big change in the force. That's very important. If we now look at the relationship, so we realized that force increased when distance decreased, and we realized that force decreased when distance increased, but that's not enough. We want the inverse proportionality. So that tells me that force is inversely proportional to 1 over r squared. That r squared is so important, all right, when we do this. You can't leave that r squared out. How do we put this all together? Well, I've now said to you that we have this relationship between all my factors. Okay? I can write it as m1, m2 over r squared. That's directly proportional to m1, m2, inversely proportional to r squared. We can't use the proportionality, so we have to introduce a constant to get rid of that. That constant is g m1 m2 over r squared. There's our equation. We're going to take a small ad break, and we'll see you in a couple of minutes. Welcome back, everyone. We're going to dive in and do some calculations now. First question. The distance between the centers of two mass pieces. Here, it doesn't matter really what the mass pieces are, but they're mass pieces, they're just weights, is 6 kilograms and 4 kilograms, and they are 3 meters apart. They want us to calculate the magnitude of the gravitational force that they exert on each other. Magnitude means it can only be size. Direction is not something I need. The thing with Newton's law of universal gravitation is that the direction's always attraction. We need to be a little careful with the way the question's worded when we put direction, but here, they only want size, they only want magnitude. Remember as well that you can't get a negative value for this equation. If you do, something's gone wrong, and you need to relook at what you've done. Okay, you can't get negatives. How do we do this? So we have the two centerpieces. This is what we're saying. We've got a mass, which is 6 kilograms. We've got a mass, which is 4 kilograms. And the distance between them is 3 meters. I want the gravitational force. As soon as I see that, I know I'm using Newton's law of universal gravitation. So F equals G m1 m2 over r squared. Do you need to remember this equation? No, because it's on your information sheet. But hopefully, if you practice enough, you'll know it in your head. Okay? Now we need to do the substitution. Big G is a constant. It's given to you as well, and that's 6,67 times 10 to the minus 11. Ish, we don't like that, but it's fine. My masses are both in kilograms, so it's going to be 6 times 4, and now the big MB. It's 3 meters squared. I see this all the time. The square gets left off. I don't know what it is about the square, but it gets left off and it gets forgotten. It feels very lonely some days. Please don't forget the square. Often what you'll do is you'll write the equation with the r squared because you take it off your information sheet. Then when you do your substitution, the square goes on holiday. You're going to get the wrong answer. You need to make sure you put it in there. Now we need to put this in our calculators. Before I do that, you also need to make a decision. Looking at the values that you've got two small masses, 6 and 4, tiny. 3 meters apart, they're actually quite far apart. that means that I'm expecting to get a small answer. So before I even do the calculation, I'm going, what sort of answer am I looking for? Because that gives me an idea when I get to the end as to, did I get the right answer? So, here we go. We have, and I know I do this slightly differently to the way you guys use your calculators, but it doesn't matter. 6.67, and it's going to be times 10 to the minus 11. I'm going to times by 6, times by 4. I get an answer, and now I'm going to divide, and here's the trick, 3 squared. Don't forget about the square. And look there, this is tiny. Final answer, 2 decimal places, so this is going to be 1,78 times 10 to the minus 10. 1,78 times 10 to the minus 10, and it is newtons. I don't need a direction, they didn't ask for it. It's very small. This isn't even a force that you would be able to experience. You wouldn't even notice that it's there, but it is there, okay? And both objects, both mass pieces are feeling the same force. Newton's third law. It doesn't disappear because now it's two small little objects. This gravitational force is a field force. It can act over a distance. We don't have to have the objects right on top of each other. You get it? We thinking through it? Let's do another question. All right. The centers of two identical balls. That identical means that they are the same in every way. They are the same physical shape, so they have the same volume. They're made out of the same material. They have the same mass. Everything about them is the same. That means I'm telling you that mass 1 is equal to mass 2. We're going to use that. They're situated 1 meter apart, and the gravitational force between them is 6,7 times 10 to the minus 9. That's quite small. We're good with that. What they want is the mass of each ball. So, let's get to the equation. We know that we're going to be using F equals G m1 m2 over r squared. Now we've got to look at how we substitute this in. Because the two balls are identical, I'm going to go mass 1 is equal to mass 2, and I'm just going to make that m. When I use the subscripts 1 and 2, I'm saying they're two different objects. By saying that those objects happen to have a mass of m, I'm making my maths a bit easier. Let's substitute in what we know. 6,7 times 10 to the minus 9. We have to use G. 6,67 times 10 to the minus 11. Now I've got m times m, and my distance is 1 squared. We like it when they use 1. It's an easy one. I'm now going to manipulate it because I need to get m on its own. Okay, so m times m is m squared. I'm going to divide both sides. 1 squared is 1, so I can ignore it. I'm now going to go 6,67 times 10 to the minus 9 divided, 6,7 times 10 to the minus 9. We're going to divide it by 6,67 times 10 to the minus 11. Ooh, that's an 11, by the way. There we go. That's the first thing I need to find the answer to. So calculator, and we go 6.7 to the minus 9 divided by 6.67 to the minus 11, and I get 100,449,751. I don't want that value because that is the square. I want, whoopsie, just m. So I need to take this value, and your calculators are great because it stores that last one, that last answer, square root of my answer, and I get 10,02, okay? Was that right? I think I missed out. No, 02. Yep. See, you've got to make sure you look at your calculators properly. It's very easy to make a mistake like I just did, and we want to avoid that. So that's 02 units. We've got a mass, kilograms. What are the mass of each ball? 10,02. I don't need to do anything else after this. Remember, if I get a negative answer, I've absolutely made a mistake. So make sure you keep that in your mind. Both masses are the same because they are identical. Not the nicest maths, but it's okay, we can do that. Hopefully this wasn't too bad. We're going to take a short break, and I'll see you in a couple of minutes. Welcome back. We're going to go straight back into doing some more equations. Here's our question. 2 marble spheres. Honestly, what the spheres are made out of doesn't matter. One is 80 kilograms, one is 50 kilograms. They are situated so their centers are 2 meters apart. So I'm giving you M1 and I'm giving you M2. There are 2 questions for this one. The first one is I want to know the force of gravitational attraction. Here, it's not saying the magnitude of the force, they're saying force. That means when I get to the end, I must put a direction. Very important. Then they give you a second question which says, calculate the force between them if the distance is diminished to 0,5. So this one is a reading thing. It's diminished 2, so that means it becomes 0.5. It's not just made 0.5 smaller. But we'll get back to that one once we finish the first one. Here we go. We have our 80 kilogram, and we have our 50 kilogram. I'm going to call this mass 1. I'm going to call that mass 2. And the distance between them is 2 meters. My first question is the force of attraction. It's gravitation. I know that I need to use F equals G, M1, M2 over R squared. I know G, remember, it's given to you on your information sheet, 6,67 times 10 to the minus 11. My first mass is 80. My second mass is 50. And my distance is 2 meters, but we mustn't forget about the square. I absolutely have to use a calculator for this one. Not because of the 80 and the 50 and the 2, but because of the constant. It's so tiny. It's difficult to work with that in our heads. And I'm pretty sure we could if we really wanted to. But why? We have a calculator. Let's use it. So, let's clear my calculator. There we go. So we've got 6.67 times 10 to the minus 11 times by 80 times by 50. That, when I press equal, that gives, maybe I put an extra bracket in there, so that shouldn't happen. So let's do that again. Got to make sure it's right. Times by 80. I put a bracket at the end of this, which I shouldn't have. That's the top end of my fraction. Now I've got to take that answer and divide by 2 squared. And we get 6,67 times 10 to the minus 8. 6,67 times 10 to the minus 8. And we know that's newtons. Again, we look at it and we go, yes, 80 kilograms and 50 kilograms seems heavy. But in terms of gravitation, it's really not. They're very small forces, very small masses. Because remember, when we look at the Earth, we don't even notice the force of attraction between us and the Earth anymore. And that's quite big. So two tiny objects like this, it's a tiny force. But we're not done with this question yet. Calculate the force. I've only got magnitude here. I have to put a direction. And here, the direction is attraction. And I know some of you are going, but how's that a direction? It's telling me how the two masses will move. They will come together. You can't give me a direction left, right, up, down. I didn't give you a diagram. And because they both experience the same force, they're going to move in two directions. The 80 is going to go to the 50, and the 50 is going to go to the 80. So attraction is fine. That is a direction for this section of work. Let's do the next one. Now they say, same situation, except my distance is diminished to 0.5. Here, like I said when we started, you need to read this question carefully. Diminished means made smaller. I said it's made smaller to 0.5, so it becomes 0.5 meters. If the question had said diminished by 0.5, then I would minus it. But they're saying to me it's becoming 0.5, so my situation changes to this. I have my 80 kilogram and I have my 50 kilogram, so that hasn't changed. But that distance is now 0.5 meters. We now remember that force is inversely proportional to the square of the distance. So if I make the distance smaller, my force must become bigger. So I've got to have a bigger answer than I had last time. Let's see if that's what happens. So force, G, M1, M2, over R squared, 6,67 times 10 to the minus 11 times 80 times 50 divided by 0.5 squared, and we take our calculators out. Let's just clear it. 6.67 to the minus 11, let's put the other one there, times by 80 times by 50, so that gives me the top half. Now I'm going to divide by 0.5 squared. Oh, look at that. Now I get 1,07, we round off to 2 decimal places, times 10 to the minus 6. Okay, and of course this is attraction again. That's not going to change because we have to have a direction. If we go back here, that force was 6,67 times 10 to the minus 8. I'm just going to put it here. Let's put it in another color. So my original force was 6,67 times 10 to the minus 8. This has gotten much bigger. I'm going to do a little bit of a trick here. And this is because I want you to see something. So if I go, and this isn't part of the answer, I'm just trying to show you something. 6,67 times 10 to the minus 8, and I divide it. Okay, I've got to do the other way around. Sorry, let's just go back here quickly. I'm doing this the wrong way around. So, and I'll show you now where I'm going. So 1,07 times 10 to the minus 6 divided by 6,67 times 10 to the minus 8. All right, so now let's put this in the calculator. So we've got 1.07 to the minus 6 divided by 6.67 times 10 to the minus 8. Oops. We're going to round that off for our purposes. So we get 16. It's not exactly 16 because I rounded off this answer. The distance was 4 times smaller. 0,5 is a quarter of 2. The force became 16 times bigger, which is right because 4 squared is 16. So it worked. Force inversely proportional to the square of the distance. Made the distance really small, made the force much bigger. Still not a force we're actually going to be able to experience, but that doesn't matter. Okay. When we look at this, you need to be able to state Newton's law of universal gravitation. Every particle in the universe attracts every other particle in the universe with a force that is directly proportional to the product of the masses and inversely proportional to the square of the distance between them. And then we have the equation. Nice and straightforward. We're done for this. Well, for now, I'll see you again next time.